Today's topic is relative motion analysis using rotating axis. Let me start with a certain example. Let's say a motion is described relative to a rotating frame. Then we need to determine the motion relative to a fixed frame. Look at this example on the right side. This small object C is kind of sliding down along this rod, okay? And then the information we have is this object C just moved along this rod 3 meters per second square and 2 meters per second with a velocity. Right now, this acceleration and velocity is described relative to a rotating frame because this rod is keep rotating. If we want to describe the velocity of C in terms of fixed axis x and y, the velocity cannot be in this direction because this is rotating. However, the information that we have is just the linear velocity, linear accelerations. That means this information is described relative to the rotating frame. So what is the rotating frame? The rotating frame is this y and this x. So just imagine that you attach this local frame onto this rod, and this local frame is rotating along with this rod, and then this motion, acceleration and velocity is described relative to rotating frame. That's why this is relative velocity and relative acceleration. And how about the bottom example? A person just running outward this big disc, and this disc is rotating at certain velocity, angular velocity, angular accelerations. Then if you know this person's velocity, okay, everything is rotating, so the absolute velocity may not be this linear. It could be different directions, something like that. However, because you're learning on surface of this disk, you only know the velocity of going out, right? So this means this velocity is expressed relative to a rotating frame if you fixed any frame onto the disk. So let's say this small x and y is attached on the disk, and if this is rotating, this frame is rotating with the disk, then the velocity you describe as linear velocity, which is just coming out of the disk, is the velocity that is described relative to a rotating frame. The problem is, in many cases, the motion is described relative to rotating frame, but sometimes we determine the motion relative to a fixed frame. In that case, how we convert those kind of relative informations to the absolute information. In this example, let's say we have a rod, but at this time this one has rotating with a certain angular velocity, okay? Color C has a linear velocity 2 meters per second. So if we want to look at this problem in this way, so first this is a rod, so this rod is rotating. Then I want to set my local, so this is your local frame or local axis, okay? So local axis is attached on the rod, okay? So as long as you describe the object C motion, the 2 meters per second square is correct because everything is rotating with the rod. But as long as you describe this motion relative to this rotating frame, it's still linear 2 meters per second, right? The information is given relative to rotating frame. Then the question is, what is the velocity of this object C in terms of relative to your fixed frame, the capital XY coordinate system? So let's just look at this one. We want to set the local coordinate frame axis on this rod. Okay, so I want to set this is x and y, and then this center, the origin of my local x is, let's say, a. Okay, and then the origin of my fixed xy coordinate system is O. So I want to differentiate the origin points for my fixed and rotating frame. Okay, then this is rotating, right? So the rod is rotating with a certain angular velocity. So the velocity of this rod, this object C, has this velocity direction, right? So this is 90 degree because this is rotating. And then what's the magnitude of this one? So this is omega r, right? But right now, let's say this is 3 radian per second square. Use capital omega, okay? So capital omega refers to the angular velocity of your rotating axis. So the velocity along this direction can be determined by the omega and r, right? So what is the distance? The r is from the center to this object C. So this is the velocity. So this is the velocity at C, okay? And this is the velocity components, okay? Components due to the rotation, okay? But we still have this velocity, right? We still have this velocity. This velocity is v c, okay? But you just describe this velocity from your A. And then what is the absolute velocity? So I need to add these two velocities. So your Vc is equal to the velocity c due to the rotation, okay, plus this linear velocity, which is the v and c from A, right? So basically the velocity of the c is the vector omega cross product and r the position vector c from A, because right now A is aligned with O, so either way should be fine, and plus the v c A, like that. That's the velocity. Then let's apply our real value to that equation. So in equations, you can ignore just this part here because the rotating axis and fixed axis is aligned. So we don't need first term. And then this is the term that we have right now. So right now we ignore the acceleration at this point. So we have only the velocity. So right now this is rotating clockwise. So our omega is minus 3k. I just used capital K because the capital K is the direction pointing out of this board. That's the direction of the angular, that's the direction of the angular velocity. And cross products, what is RC? So my R is from here to here. So my R is from here to here. That's my R vector. So that's the 0.2. And then what's the direction? So right now the unit vector of your local axis is small I and capital small j, and the unit vector for fixed is capital I and capital J. So I just used the small letter I because this is 0.2 along this my local coordinate system. And plus, and then what is this one? This is the velocity expressed relative to your rotating axis, which is 2 because 2 is given. And the what direction? I. So if you just do the cross product, so K cross product I is Ki is J, okay? So that's why negative 0.6 J and 2I. So these are the answer, okay? But right now, your answer is expressed relative to rotating axis because we are still using small I, small j. So if you want to express your answer in terms of capital I, capital J, which is fixed onto my fixed axis, you can simply change I, small ij to a capital IJ. So how do you convert the capital small I to capital I? Let's say X and Y, and then this is I, and this is now let's look at this. This is ij and this is small ij. So if you want to express small I in terms of capital IJ, then you can simply break your small I to the I axis and to the J axis, like that. So if you break down the I component to the X axis, then this one should be the length of your unit vector is 1. So 1 cosine theta and I capital, and then the Y direction is negative, so negative sine theta J, right? How about this one? So if you want to break down this one into X and Y, your J is equal to, this is theta right now, your J is sine theta I capital, and then plus cosine theta capital J, right? So this is just a relationship between small ij and capital IJ. So as you see that here, the small capital I, capital J is just replaced by this one to get the answer as capital I and J unit vector. So this is expressed with respect to a fixed axis. Okay, let's add our acceleration term. So the rod is rotating at this acceleration. Also, there's also linear accelerations for this object C, which is expressed relative to rotating frame. In this example, in addition to the velocity, we have a acceleration as well, which is omega dot, which is 2 radian per second square. And then this one too. So we have 3 meter per second square, and this is acceleration C with respect to A. Then this rod is rotating, so there might be the acceleration of tangential accelerations and normal component of acceleration, right? So tangential acceleration is omega dot cross product R C, okay, and normal component is omega square, okay, and just R, right? Omega square and R. But right now we have another acceleration, this one. So you have to write down AC, with AC should be the tangential term and normal term due to rotation, right? And plus we have to add this acceleration as well, which is AC with respect to A. So if I just write down again, this one should be omega dot cross product RC with respect to A, and then minus omega square R vector CA. This is tangential, this is normal components, and plus ACA. But this is not correct. Actually, we have to add one more term. Okay, why? Let me explain why we need add another term. So this is axis, and this is rod, and then this is object C. So object C has a velocity which 2 meter per second, and then later, okay, this is still kind of rotating, but because of this velocity, c kind of shifted to the end a little bit more, right? Then if you think about the velocity due to the rotation, initially the acceleration is omega r, but right now since the rod C is kind of keep moving, at this point your r is increasing, right? So that's why the velocity should be omega r plus delta r, because this C just changes position. Your linear velocity is still 2 meters per second, but your velocity due to the rotation has been increased. That's why the velocity changed. The velocity changed due to acceleration. That's why that acceleration must be included into this term. Okay, that is determined by 2 times omega, you mean angular velocity, and the linear velocity. So this term explained the velocity change due to the rotation, and we call this is Coriolis term. The example. So right now we included this acceleration term here. So our equations looks more complicated. Let's ignore this one because our axis of rotating frame is aligned with the fixed one. And then this is tangential component of acceleration due to rotation. This is tangential normal component of acceleration due to rotation. And this is linear acceleration relative to rotating frame. And this is the term, Coriolis term, because as this one rotating, the velocity that perpendicular to the rod direction has been is increasing. That's why we have to add this term. Okay. So if you just plug all the information to this equation, right now our angular velocity, angular acceleration is k direction, and then you know that this position vector of C from O is 0.2 small I, because your 0.2 is pointing from here, and then everything else is same. So I think this one should be 2 times, and then minus 3k cross product 2i, and so on. So you have this answer for acceleration. So acceleration of C is meter per second square, like that. But again, if you want to change ij to capital Ij, then you can just simply convert small I to ij, which means we want to express your answer in terms of fixed frame, which is ij.